Imagine standing at a shoreline where the water looks thick, stained, and strangely alive. Fish are gasping near the surface. Shellfish beds are closed. The smell is sharp, almost chemical. What you are seeing may be a harmful algal bloom, often shortened to HAB. People sometimes call marine blooms red tides, but color alone is not the key issue. The real danger is what the bloom does to the ecosystem. Some blooms release toxins that poison fish, marine mammals, birds, pets, and humans. Others may not be toxic at all yet still become deadly by stripping oxygen from the water. In both cases, the bloom can destabilize food webs and shut down fisheries, tourism, and local livelihoods. A harmful bloom is not just too much algae. It is a biological event with cascading consequences. To understand why HABs are so serious, we need to follow the full chain: how they start, how they grow, how they kill, and why recovery can take far longer than most people expect. At first glance, algae seem harmless, even beneficial. In normal amounts, microscopic algae are foundational producers. They convert sunlight and nutrients into energy that supports aquatic food chains. The trouble begins when conditions shift from balanced productivity to runaway growth. During a bloom, algae multiply so rapidly that they dominate the water column. Scientists do not always define harmful blooms the same way. One definition focuses on toxin-producing species. Another includes any bloom that causes ecological harm, especially severe oxygen depletion. That distinction matters because communities often wait for confirmed toxins before treating a bloom as a crisis, even though non-toxic blooms can still trigger mass mortality. HABs can appear in freshwater lakes, estuaries, and open coastal systems. They may last days, weeks, or in some cases months. A long-lasting bloom can repeatedly stress the same habitat, reducing resilience season after season. So the central lesson is this: harmfulness is about impact, not just species name or watercolor. If a bloom drives ecosystem collapse, it is harmful whether or not toxins are detected. One of the most destructive mechanisms is oxygen collapse. While the bloom is active, dense algal layers block light from reaching submerged plants. Those plants weaken, reducing oxygen production below the surface. Then comes the second blow: as bloom cells die, bacteria decompose the organic matter. That microbial decomposition consumes dissolved oxygen at high rates. The result can be hypoxia, meaning dangerously low oxygen, or anoxia, where oxygen is nearly absent. Fish and invertebrates either flee or suffocate. If the affected zone is broad or persistent, escape routes disappear and die-offs intensify. This is how dead zones form, not because water suddenly becomes poisonous in the usual sense, but because the habitat can no longer support aerobic life. Importantly, the worst oxygen stress often arrives after the bloom peak, when observers think the event is fading. That delay creates a policy challenge. By the time water looks clearer, biological damage may still be accelerating underneath. Monitoring must therefore continue beyond visible bloom decline, or managers will underestimate impact and respond too late. Toxins add another layer of risk. Some algal species produce compounds that attack nervous systems, livers, or other organs. These toxins can move through food webs, concentrating in shellfish or small fish and then affecting predators, including humans. Symptoms in people range from gastrointestinal distress to neurological effects, depending on toxin type and exposure route. But toxicity is not the only pathway for harm. Dense blooms can also cause mechanical stress, such as gill irritation in fish, making respiration harder even before oxygen falls. In real events, these mechanisms overlap. Mild toxicity, reduced oxygen, and physical stress can combine into severe mortality. That is why simplistic messaging like "it is only an algae event" is dangerous. HABs are multi-pathway threats, and each pathway can dominate in different places or times. Effective response plans must assume complexity from the beginning. If authorities focus only on one hazard class, such as toxin testing, they may miss urgent oxygen crashes or sublethal stress that weakens populations long before visible die-offs occur. So what fuels these explosive blooms? The core driver is eutrophication, a nutrient overload in water. Two nutrient groups are especially important: fixed nitrogen forms like nitrate, ammonia, and urea, and phosphorus, often measured as phosphate. In healthy systems, nutrient supply and biological uptake are roughly balanced. Under heavy runoff, that balance breaks. Agriculture is a major contributor through fertilizer losses from fields. Urban and suburban landscapes add lawn fertilizer, stormwater pulses, and wastewater leakage. Sewage and livestock waste can deliver concentrated nutrient loads, especially after rainfall. Industrial discharges may also contribute in specific watersheds. Once those nutrients enter rivers, estuaries, and coasts, they act like growth accelerants for opportunistic algae. Crucially, nutrient timing matters as much as nutrient amount. A large pulse arriving during warm, stable conditions can trigger rapid bloom initiation. This means prevention is not just about annual averages. It is about reducing peak delivery events, especially the runoff surges that follow storms, irrigation return flows, or sewer overflows. Climate and physical water dynamics decide whether nutrient-rich water actually blooms. Warmer temperatures generally favor faster algal growth and can lengthen bloom seasons. Stratification, where warm surface water sits over cooler, deeper water, can trap nutrients and cells in sunlit layers that support rapid reproduction. Low circulation means less dilution and fewer disruptions, giving blooms time to organize and expand. In coastal zones, wind patterns can create Langmuir circulation, parallel surface streaks that physically concentrate algae and intensify local exposure. Storms play a paradoxical role. A major storm may temporarily mix water, but it can also deliver huge nutrient pulses from land and trigger later bloom growth. Upwelling can bring nutrient-rich deep water to the surface, acting as a natural bloom trigger even in less developed regions. This is why HAB causation is often contested. Some blooms are clearly linked to human nutrient enrichment, while others reflect natural oceanographic cycles. In practice, modern events often combine both, natural triggers acting on human-amplified nutrient baselines. That combined pressure helps explain why many experts report blooms becoming larger, more frequent, or more disruptive in multiple regions. Global climate change is not a single switch that causes every bloom, but it shifts background conditions in ways that increase risk: warmer waters, altered rainfall, stronger runoff extremes, and longer periods suitable for growth. Coastal development adds another stressor by changing drainage patterns and increasing nutrient delivery to nearshore waters. Aquaculture can contribute local nutrient enrichment when feed and waste accumulate. The key point is that HAB trends emerge from systems-level interaction, not one isolated variable. Debating whether a specific bloom is natural or human-caused can be misleading because both forces can operate together. A naturally favorable season in a nutrient-loaded watershed produces a very different outcome than the same season in a well-managed one. For policy, this means uncertainty about any single event is not a reason for inaction. Risk management should target controllable amplifiers, especially nutrient inputs and vulnerable coastal designs, while planning for climate-driven volatility. The economic footprint of HABs is often underestimated because costs are spread across sectors. Fisheries lose harvests when fish die or stocks move away from low-oxygen water. Shellfish operations face closures during toxin alerts, with income losses that can persist after waters reopen. Tourism drops. When beaches smell foul, water looks unsafe, or health advisories dominate headlines. Local governments bear emergency monitoring and cleanup costs, while healthcare systems absorb exposure-related cases. For small coastal communities, repeated blooms can erode trust in local seafood, damaging market demand beyond the event window. Ecological losses are equally profound: habitat degradation, food web disruption, and repeated stress on already pressured species. Recovery is not immediate after visible scums disappear. Rebuilding oxygen regimes, plant cover, and population structure can take seasons or years. That lag creates a political blind spot because public attention fades faster than ecosystem repair. A robust response therefore needs long-horizon funding and communication, not just short-term crisis optics when a bloom first appears. Monitoring is the bridge between science and action. Agencies like NOAA already project elevated bloom risk in some regions, but local preparedness depends on dense, timely data. Effective systems combine satellite imagery, in-water sensors, lab analysis, and field reports from fishers and residents. Satellites can detect surface chlorophyll anomalies over broad areas. Fixed sensors track dissolved oxygen, temperature, and nutrient trends in near real time. Lab testing confirms toxin profiles and species composition, which is essential for public health decisions. Community reporting adds rapid situational awareness where formal infrastructure is sparse. The goal is not perfect prediction, it is early warning with enough confidence to trigger proportionate action. Importantly, monitoring should continue through bloom decline because oxygen crashes and secondary effects can peak later. Data integration also matters. Separate dashboards for toxins, oxygen, and hydrology create fragmented response. Integrated alert systems help managers see compound risk and communicate clearly where exposure is rising, what activities are restricted, and when conditions are genuinely improving rather than only looking better at the surface. Can we stop harmful blooms completely? In most systems, no. But we can reduce their intensity, duration, and damage through layered intervention. First, cut nutrient runoff at source, precision fertilizer application, buffer strips, wetland restoration, improved manure management, and stormwater controls that slow and filter flows. Upgrading wastewater treatment to remove more nitrogen and phosphorus is often high impact where infrastructure is aging. Second, improve water body resilience by restoring circulation pathways and reducing stagnant hotspots where feasible. Third, deploy targeted response tools carefully. Chemical treatments may suppress blooms in some settings, but they can create trade-offs, including downstream oxygen stress from killed biomass. Engineering options like additional reservoirs or flow management can help in specific watersheds, yet they are not universal fixes. Finally, governance must align monitoring, agriculture, urban planning, and public health, because HABs cross agency boundaries. The practical win is risk reduction, not elimination, fewer severe blooms, faster detection, better advisories, and stronger ecological recovery when events occur. If there is one takeaway, it is that harmful algal blooms are not random accidents we simply endure. They are warning signals from overloaded water systems. Nutrients, warming, circulation, and land use interact to push ecosystems past stability thresholds. Once crossed, the damage can persist long after the bloom itself fades from view. The good news is that the same chain that creates HABs gives us intervention points, reduce peak nutrient pulses, track oxygen and toxins continuously, design coastal growth with hydrology in mind, and communicate risk early and honestly. Communities that treat blooms as recurring system stress, not isolated surprises, are better positioned to protect health, livelihoods, and biodiversity. HABs may be biologically complex, but the strategic direction is clear: prevent where possible, detect early, respond adaptively, and recover intentionally. Water does not become dangerous overnight without causes. And it does not become resilient again without sustained choices. If you found this helpful, please like this video and subscribe for more explainers.